All right, welcome to the spring 2022 semester of the New England Dynamics and Number Theory seminar. And today we're happy to have Akshat Das from Texas. And his talk is about the adelic version of the three-gap theorem. It's yours now.
Thank you so much. Good afternoon, everyone. I would like to begin by thanking the organizers, especially Dr. Kleinbach, for this wonderful opportunity to talk about my most recent project, especially during this time when I am actively trying to look for a postdoc position. So today I'll talk about an adelic version of the three-gap theorem, and this is jointly proved by me and my thesis advisor, Dr. Alan Haynes. So I'll start by talking about the classical version of the three-gap theorem. So let's consider the unit circle R mod Z and take a fixed real number alpha of your choice and a natural number capital N. And then we construct a sequence of the fractional parts of K alpha, where K is going to run from 1 till capital N. And we denote this by xi k. And then what we do is we plot all these xi k's on the unit circle. So once we plot all of them, what this does is that it divides the unit circle into component arcs. And the length of each of these arcs represents a particular gap length. So we use delta kn to denote the kth gap, which is going to be the distance of xi k from its nearest neighbor to the right. So this is important that we are looking for the nearest neighbor to the right of xi k for this particular gap length. And then the classical version of the three-gap theorem states that for any choice of alpha and natural number capital N, the upper bound for the little g and alpha function, which is going to count the number of distinct values that we have for these gap lengths, is equal to 3. So this is, of course.
Excuse me, just wanted to mention that the notion of left and right on the circle is kind of convoluted. Maybe you should say in the counterclockwise direction or something like this.
Yes, in the counterclockwise direction.
You turn and then right turns to left and vice versa.
Yes. Yeah. Thank you. Okay. So it is important because I'll come back to it later when we define the notion of nearest neighbor distance in our setting. Okay. So yeah, and this bound is best possible and it is attained. So here's a simple illustration of what is going on. So let us take alpha to be square root of 2 and capital N to be equal to 12. Then we are plotting the points starting with 0 all the way up to fractional part of 12 alpha. Then you can see that the first distinct length, which is the shortest one, is denoted by the red color, which is between 12 alpha and 0. The next distinct length is colored in blue. And for example, that's between 5 alpha and 10 alpha, or say 3 alpha and 8 alpha. And then the third and last distinct length is colored in purple. And that is, for example, between 10 alpha and 3 alpha, or 8 alpha and alpha. So you can also see that the purple length is actually the sum of the red and the blue length. So this is also quite a lot of times stated in the statement of the theorem that the sum of the first two, sorry about that, sum of the first two distinct lengths is equal to the third and the largest distinct gap length that we have. Okay, so this was just a small illustration. And this theorem was first proved independently by 3 different authors in the late 1950s. And from then onwards, it has been reproved a lot of times and also generalized in a lot of ways. The one proof that we are interested in was actually given by Dr. Marklof, who I am happy is here, and Andrew Strömbergsson. And this was given in 2017, where they reprove the classical version of the three-gap theorem using the space of two-dimensional Euclidean lattices. So the advantage of this approach is that we can then use this to generalize things in higher dimensions. So this is a nice approach to gaps problems in Diophantine approximation. And what we are doing in this project is using an adaptation of this process to the adeles to prove a natural generalization of the three-gap theorem for the adelic tors. So that is our goal. But before I start talking about our work, I'll set up some background and notation. So let's start with a non-zero rational number A. Then for any prime number P, we are able to uniquely represent it in this form. And the periodic absolute value of A is defined to be P to the power of minus M. And by convention, we take the periodic absolute value of 0 to be just equal to 0. Then, as we have that the reals are the completion of the rationals under the Archimedean absolute value, the completion of Q under this periodic absolute value gives us the field of periodic numbers, which is denoted by QP. And another way of looking at the periodic numbers is in this form of a formal Lorentz series, where all the elements are coming from 0. So all xi's are from 0 to p minus 1. Now, if we consider the particular periodic numbers whose periodic absolute value is less than or equal to 1, then that gives us the ring of periodic integers, which is denoted by ZP. Okay, so now the next thing that we have is the topological ring of adeles over Q, which is denoted by A. And this is a collection of these infinite tuples where the first component in the Archimedean place is coming from the reals, and all the other non-Archimedean places are indexed by all the primes. And the elements here are coming from QP for every prime P, where the condition is that for all but finitely many of these alpha P's need to be in ZP. So it is important to note that this product is over all the primes P. And this has the restricted product topology with respect to ZP, and addition and multiplication is just defined pointwise for each component of the elements that we have over here. Okay, so this product was over all the primes. So how about we take a particular non-empty subset of the primes of our choice and denote it by script P. So then the topological ring that we get by projecting the adeles onto this particular place, where the first place is denoted by the Archimedean place, and then all the others are indexed by the particular primes that you have in this set P. So this gives us AP, which is another topological ring, and this is endowed with the final topology with respect to this projection. Now, gamma P can be diagonally embedded into AP using this injective homomorphism, which basically takes any element of gamma P and then puts gamma at all the places that we have. And this can actually be identified with itself. So gamma P can be identified with its own image. And this is a discrete subgroup of AP. So this finally helps us to go ahead and define the adelic torus, which is denoted by XP, and it is the quotient group AP mod gamma P. And this is a nice connected, compact, metrizable, and abelian group. And finally, for this comment that I have in the end, I was talking about this project with Dr. von Kleimenhager, and we were trying to think about how one could visualize this p-adic solenoid. So if we consider the most basic case, which is the two-adic solenoid, so that will be R cross Q2 mod Z 1/2, then this is actually homeomorphic to the Smale-Williams solenoid. So this is a nice, just a comment about if you want to visualize this from a topological point of view for the most basic case. All right. So before I move on, here's a quick summary of all the background and notation that I just talked about. So we have QP to be the field of p-adic numbers, and ZP to be the particular ring of p-adic integers. And then the adeles are this collection of infinite tuples where we are taking a product over all the primes. And then we are taking a particular subset, a non-empty subset of the primes P, which we denote by script P. And then we have the projection of the adeles onto this, which is the AP. And then gamma P is the discrete subgroup of AP, which then helps us define the adelic torus, which is the quotient group AP mod gamma P. Okay, so I think now I'm done with the background details. The problem that we are trying to approach over here and solve depends a lot on what the metric is on our space. So let's think about what the metric should be. So to start off, for reference, we are using this to denote the regular usual Archimedean absolute value on the real numbers. Now, first of all, let's think of a metric on AP. So the metric on AP is defined as follows. And if the cardinality of P is finite, then this is nothing but the maximum metric. And also in the case when it is not finite, this is a natural choice of metric on AP. And this ends up giving the restricted product topology on AP. And using this, we can go ahead and define a metric on the adelic torus, which is defined as follows. So we will take the minimum over all the elements of gamma P. Now, at this point, we have a proposition that we prove, which makes life a bit easier for us, because what we prove is that we don't need to take the minimum over all the elements of gamma P. It is enough to just consider gamma to be equal to 0, 1, and -1. So if we take the minimum over that, that should be good enough. And this gives the quotient topology on the adelic torus. Okay, so that was the description of the metric that we have. I think this is a good.
Can you explain what happens if you don't divide by P? Why is it important to divide by P for the infinite case?
This was the natural choice of metric that we were taking from a different paper where they needed it. So
so why don't you use the second metric also in the first case?
Oh yeah, it does. It's equivalent. Yeah, of course. Of course,
it will be equivalent in that particular
case.
Case.
If that's what you just like. I'm just curious what happens if you don't divide by P, but we can. Okay, go on.
Yeah, when I was first thinking about it, I was a bit curious, because like if we have the case when the cardinality of P is infinity, then I wasn't sure if this maximum works, because we're taking a maximum over an infinite set. But then I think it is well defined. But yeah, I have not particularly thought about why we would need that.
Okay.
Okay. Okay. So I think this is a good point to a good stage to talk about the main theorem that we have. So I'm going to use a lot of notations that I already had for the classic case. So again, let's take a particular element alpha from AP and a natural number capital N. Then we take Sn alpha to be the collection of all the fractional parts of n little n alpha, where little n is going to run from 1 to capital N. And these are the points that we're going to plot on the torus. And next, what I'll do is define the notion of nearest neighbor distance. So here is where things are slightly different from the classical case. There in the classical case, as I have pointed out, we have the notion of looking for the nearest neighbor in a particular direction. But here, delta n and alpha for any little n is just defined to be the distance of xi n from its nearest neighbor. So there is no particular notion of looking in a particular direction. We are just looking for the nearest neighbor of xi n, and things still work out in a much similar way without that as well in our case. Okay, so once we define the nearest neighbor distance, we again have the little gn alpha function, which is going to count the number of distinct values that we have for the nearest neighbor distance as n runs from 1 to capital N. And the theorem that we have is that irrespective of the choice of set of primes P that you have, for any alpha in xp and any natural number capital N, we have that the upper bound of the little g and alpha function is again 3. So there are at most 3 distinct nearest neighbor distances. And there's a second part to our proof where what we do is we show that for any choice of the set of primes P, there will always be an example of alpha and capital N where the little g and alpha function actually takes the value 3. So this is the best possible bound, and it is adelic. So that is the second part of our proof. Okay, so the idea is that we want to express this little g and alpha function, which is counting the nearest neighbor distances, in terms of a function on a space of lattices. So that is where we are borrowing the approach from the classical version proof that I talked about. So we need a space of lattices. So let's consider G to be SL2 AP and gamma to be SL2 gamma P. So then this gives us the space of lattices that we want, and we can think of it as a space of lattices of determinant 1 in AP squared. Another way of thinking about it is that it is the gamma P span of rows of a matrix in G. Okay, so now that we have a space of lattices, the first step in this whole reformulation process is to rewrite the nearest neighbor distance in terms of a function on this space of lattices that we have. So in order to do that, what we first do is we replace, for some technical reasons in the proof, we replace n with n plus half, and we denote it with n plus. So the next step that we do is, in place of m minus n, let's take it to be equal to k. So then we can rewrite the nearest neighbor distance in this form. So we are basically taking the minimum over the absolute values of k alpha plus gamma, where it is important to note that k is lying in this strip of length 1. So this is the important part. So there is a lattice here somewhere in the background, and we need to figure out what that lattice is. So that is the most immediate goal over here. So towards that, let's go ahead and define
Excuse me.
this lattice. Yes?
Could you go back to your previous slide? The previous one. So why is the second line? Can you explain again why the second line is equivalent to the same to the third line?
So basically, we are dividing by n plus, and I think there should be a 1 over n plus on the outside as well. So what we did here was that we divided this whole thing by n plus.
But then k should also be divided by n plus in the middle, no?
Yeah.
Probably it's just a misprint.
Yes, you're right. I think that is a typo. I should have, I forgot to change that. So let me go to the next slide and I will show you how the things are equivalent. Sorry about that. Yeah, I should definitely fix that over there. So there should be a 1 over n plus over here. And the k should also be a bit different over there. Okay, sorry. So so what we are doing first is defining a lattice over here. So for each non-zero rational number t, let us define this lattice in G, which is t inverse t alpha 0 t. So if we take the particular case where t is equal to n plus, and then left multiply this particular lattice an plus alpha with an element of gamma p squared, then once we do this computation, we end up with a lattice point. Now, this lattice point is very important, because if we look at the last version, or the most recent version of the nearest neighbor distance. So I'm going to just take this and put it over here for a sense of reference. So, oh, sorry. Yes, okay. All right. So if you look at the quantity over which we are minimizing, that is very similar to the second component of this lattice vector. So the idea is that if we look at this computation and then look at the most recent version of the nearest neighbor distance that we had, then what we get is that we can rewrite the nearest neighbor distance in the form of this lattice an plus alpha. So I think I have things a bit in the correct form over here. So what we can rewrite the.
Sorry, I think you need to divide the k in the middle by n plus, and in the front there shouldn't be a 1 over n plus. That's still good. If you can.
Yes.
So the k in the middle should be divided by n plus, and then everything's fine.
Yeah, that's what I was trying.
When you then go to the next step, you can put your 1 over n plus in front and an n plus inside the first term, and then everything is good. But there shouldn't be the 1 over n plus without the n plus in the middle.
Okay, thank you so much for that. Okay, so yeah, so using the last step that we had and this calculation that we just did, we can rewrite the nearest neighbor distance in this form. So what are we doing over here? So we have this lattice, and we are taking a particular collection of lattice points where there is this restriction on the first component of the lattice vectors. And then what we do is, once we have this particular collection of lattice vectors, we take the absolute value of the second component of these lattice vectors and take the minimum over that. So that is how we are rewriting the nearest neighbor distance. But then the point is that this is in particular for the lattice an plus alpha. But what if we want to just think of it in a more generic form? So the next step is to take any lattice element m and any real number between 0 and 1, which is t, and a particular natural number z. And then we define this set of lattice points qmtz. So this is going to be the collection of lattice points here, where again, the restrictions on the first component are the same as that we had for the most recent version of the nearest neighbor distance, but in a more generic form. So the real component is going to be in this strip of length 1, and we have these restrictions on the non-Archimedean places for the first component of all the lattice vectors. And then we define the function f on the space of lattices. And what this does is, again, does the same thing which we had in the nearest neighbor distance. So it is going to look at all these particular lattice points and the absolute value of the second component and take the minimum over that. So this is a function that we have defined on the space of lattices. So now we are getting close to our goal of reformulating the nearest neighbor distance first in terms of a function on the space of lattices. So before we go ahead, it is important to make sure that this function f is actually defined, and it does see some such lattice points. So for that, we have an adelic analog of the Minkowski's convex body theorem, which was first independently developed by McFeet in 1971, and then later by Bombieri and Waller in 1983. And this is used to prove that f is indeed well defined on our space of lattices. So now this function f is important because if we again consider the particular case where our lattice is an plus alpha, then comparing with the most recent version that we had for the nearest neighbor distance, we can go ahead and conclude that the nearest neighbor distance can be written as 1 over n plus times f, where f is where we are considering the particular case where our lattice is an plus alpha and our number t is n over n plus. So this completes the first step, where we are able to rewrite the nearest neighbor distance in terms of the function, in terms of a function on the space of lattices. But the ultimate goal was to write the function little g and alpha, which was counting the number of distinct nearest neighbor distances in terms of this, in terms of a function on the space of lattices. So for that, let's go ahead and define script g for any lattice m and natural number z. So what this does is that, so if you recall, the set qmtz was defined for a particular value of t. So now what we are going to do is we let the t vary between 0 and 1 and see what are the distinct values that f takes. So then the script g function is going to calculate the number of distinct values that the function capital F is going to see. And finally, for a particular value of n, so for a particular value n in the natural numbers, let's define script gn, which is going to be the value, the number of distinct points that the function f takes for the particular case when t is equal to n over n plus. So this is again our particular case. So the next thing that we do is we prove a proposition, which is very, very important going forward, because what we are able to prove is that the little g and alpha function, which is calculating the number of distinct nearest neighbor distances, is actually going to be equal to the value of script gn function for the particular case when m is an plus alpha. And then the broader inequality that is very useful for us is that it is also going to be bounded above by the value of the script g function for the particular case when we take the lattice to be an plus alpha. So this particular inequality is extremely important because this reduces our problem of finding an upper bound for the little g and alpha function to finding an upper bound for the capital G function. Because if we are able to prove that the capital G function for this particular case of m being equal to an plus alpha has an upper bound of 3, then we are also able to prove that the little g and alpha function has an upper bound of 3. So this is how it is helpful. And the another important thing that we prove as a next step is that this function script g is always finite. So for any choice of lattice m, this function will always be finite. So here is the main is the theorem that we prove, and this helps us prove the main result that we were looking for. So for any choice of prime numbers p and for any lattice m, the upper bound for the script g function is less than or equal to 3. So this is a much more generalized thing that we are proving. And this also then helps us using this inequality prove that the upper bound for the little g and alpha function is also 3. Okay, so I think now I'll go ahead and talk about the first part of the proof where we are proving the upper bound. So first of all, again, if you recall, the script g function was calculating the number of distinct values that capital F takes as you let t run from 0 to 1. So this set qmtz was a particular collection of lattice points for a particular value of t. So let's define qmz, which is going to be the union of all such special lattice points that we see as t runs from 0 to 1. Then, because we were able to show that the script g function is actually finite, we can go ahead and assume that it is equal to some natural number k. So what does this mean? So again, the script g function is calculating the number of distinct values that the function f is taking. So if this is equal to k, then what it means is that there were k distinct lattice points that the function f was able to see, because the values of function f are absolute value of the second component of those lattice points. So this means that there are k distinct lattice points. Let us name them as u1, v1, going up to uk, vk in this collection qmz, which the function f is actually seeing. So let us organize, just for the sake of organizing these gap lengths or nearest neighbor distances in a good and proper manner. We have these 3 assumptions. So the first assumption is basically just organizing the gap lengths in increasing order. And then the second and the third conditions are ensuring that these are going to be the only distinct lattice points that the function f sees, and that the function f actually also takes these values. So these are a set of technical assumptions just to make sure that we have organized the particular collection of lattice points properly. Okay, so if we wanted to prove that the upper bound of the capital G function is 3, then we basically want to prove that k is less than or equal to 3. So the next thing that is very useful for us to prove this is the symmetry of the lattice. So what that means is that if the lattice point uv is in our collection, then automatically we can also assume that minus u and minus v, that particular lattice point, is also in this collection from the symmetricity of the lattice. So what this means is that now when we are choosing our collection of lattice points, which I had u1, v1 going up to uk, vk, we can make sure that all the real components of the first component of the lattice point are non-negative. So this result helps us assume this. So now the task of proving that k is less than or equal to 3 can be divided into two parts. So what we do is we take k to be equal to k1 plus k2, and then the bound for k can be determined by thinking about the bounds for k1 and k2. Okay, so what are k1 and k2? So first of all, k1 is the number of lattice points u1, v1 going up to uk, vk, where the real component of the first component is less than half. So in order to prove the upper bound for k1, a very important lemma that we have is that if there is a lattice vector or a lattice point in QMZ, which has this property that the real component of the first component is less than half, then the value of f for this particular collection will always be bounded above by the absolute value of the second component. So this is a very important proposition that we have. And if you want to think about it, a very vague visualization in the Archimedean place can be thought about in this way, that if I have so if I have ui infinity, right, this is the real component of the first component, and this is between 0 and half, then minus ui infinity is also over here, which is going to be between minus half and 0, which is what we have from here. So now our strip is of length 1, right? So what I'm trying to say over here is that if our strip, so our strip is going to run between -1 and 1. So a strip of length 1, and it is going to keep going between -1 and 1. So suppose that, let me extend this here, and I have -1 here, and I have 1 somewhere here. Then what is happening is that if my strip is at the extreme end over here, then also I'm going to see this vector. And even if I'm on the other extreme end, I'm still going to see this vector. So this is just a vague visualization of why this proposition could be true, which is that it is always going to see this particular vector. So the function, the value of the function capital F is always going to be bounded above by the absolute value of the second component, where of course the first component's real component is less than half. So this is a very important lemma. And using this lemma and the assumptions that we have for our collection of lattice points, we are able to prove that k1 is less than or equal to 1. So there is at most one lattice vector that we can have which has this particular condition. Okay, so now we have an upper bound for k1. It is 1. So next, what we want to do is think about an upper bound for k2. So what is k2? K2 is going to be the other part of it, which is that we consider the collection of lattice points for which the real component of the first component is going to be between half and 1. So this is these are the other collection of vectors. So this is, of course, k1 and k2 make it exhaustive. And if the upper bound for k2 is 2, then we are okay. So if K2 is less than or equal to 2, then everything is good. We will have K to be less than or equal to 3. So now the question is, what happens in the scenario when K2 is either 3 or bigger than 3? So that is the most important question. So we have this condition that all the UI infinities, which are the first components of the the real components of the first component, are non-negative. And then using another set of calculations that we have, computations, where we are using the strong triangle inequality in the non-Archimedean places, so the places which are indexed by the primes, we are able to prove that if there is indeed a scenario where K2 is bigger than or equal to 3, then there is only one possibility, which is that K2 is equal to 3 and K1 is 0. So then all the three vectors, or there are going to be three distinct lattice vectors which will have this condition, and there will be no lattice vector which has this condition. So what this does is finally proves that K1 plus K2 will always be less than or equal to 3. So this helps us finally come to the conclusion that the upper bound for K is equal to 3. And again, to recall, K was the value of the script G function. So this means that the script G function is bounded above by 3. So we have proved our intermediate theorem. And this helps us prove the first part of our main theorem, that the little g and alpha function has an upper bound of 3. So this is the conclusion of the first part. So any questions? Any other questions so far?
Do I understand it correctly that if you so your argument also works if there are no prime numbers in the classical Marklof-Strömbergsson case, right? So it's just their proof, or is it something different?
So can you? Sorry, I didn't.
No, I'm just asking. Suppose the number, suppose the set P of prime numbers is empty.
Yes.
Then
I think the classical case should be fine.
Yes. So your proof also works in this case.
Yes.
And it's the same proof as in the Marklof and Strömbergsson paper, or is it different?
So, it's similar. So it's an adaptation of what they are doing, but the idea is the same. So I think the part that I was talking about of the strip moving around is probably a nice explanation of what is happening in that case. And so that's why I was trying to give a very simple visualization of what could happen. But there are a lot of more complications involved over here, because we also have the non-Archimedean places in our particular case over here.
Okay.
Okay, so this next part is the fun part, I think, because we really like doing this part where irrespective of the collection of primes that you give us, we will always have an example where where the little g and alpha function takes the value 3. So this is what took us a lot of time. So we are dividing the whole scenario into two parent cases. The first is that because everything, including the proof, works a little differently based on if the cardinality of the set P is finite or not finite. So because if you recall, the metric is a bit different. So the proof also works slightly differently in both the cases. And then the examples are also different for both those cases. So first of all, I'm going to consider the case when we have the cardinality of script P to be finite. So then we are dividing this scenario into three separate subcases. So the first subcase is as follows. So let's take the first subcase is that the script P is singled at set 2. So in that scenario, if we take alpha to be this vector, and if we take n to be capital N to be 52, then by direct computation, we are able to show that we have three distinct nearest neighbor distances, which I have here. And so this indeed shows that for this particular case, the the little g and alpha function is equal to 3. Okay, so the other two subcases are that the set P is equal to the singleton set 3. And the third one is, of course, exclusive of the first two. So what we have is that we have a finite set of primes where the product of all the primes is at least 5. So the first two cases, we are able to just get the nearest neighbor distances by direct computation. But here is what we do for the third case, which is much more generic. So if we have the scenario where this finite set of primes has the condition that the product is at least 5, then what we do is let's take capital N to be equal to this product plus 1. And then we define the vector alpha as follows. So in the Archimedean place, we have this. And for all the non-Archimedean places, we have -1. So then again, we can see that the first distinct nearest neighbor distance that we get is going to be the maximum of 1/4 and 1/p1. And this is less than equal to half. The second one is obviously going to be a little bigger than 3/4 because this is 3/4 plus 1/4 times the product of the primes. And then the third distinct nearest neighbor distance is 1. So we have 3 distinct nearest neighbor distances. And again, this shows that the little g and alpha function is going to be equal to 3. So of course, the reason we have those two first small subcases is because if we try to use this example for those two particular cases, then the capital N value comes out to be very small and is of no use to us. And that's why we have those two first two cases stated separately. And then this is the more generalized version. Okay, so this is just the examples for the case when the set of primes is finite. Now comes the more tricky part where the cardinality is not finite. So you can have any arbitrary collection of the primes. So in this case, we have 4 different subcases. So here is the first subcase where we assume that the set P has 2, but it does not have 3. So it's going to be 2 and then for, any number of primes, but 3 is not in the set. Then the number at the Archimedean place is going to be 8/49. And on the first non-Archimedean place, we'll have -1. And it's going to be 0 for all the others. And there is a specific comment about the case when 5 is in this set. So if 5 is in this set, then we will take it to be equal to 3. So if 5 is there in this set of primes, then at that non-Archimedean place, we are taking 3. If it is not there, then everything else is just going to be 0. So this kind of highlights the difficulty that we had, because it is very difficult to construct an example which is going to work for an arbitrary collection of primes. So yeah, that is why I pointed it out over there. And then again, we have 3 distinct nearest neighbor distances, which are given over here. So this again shows that the little g and alpha function is equal to 3 for this particular case. Okay, so there are other 3 subcases. The second one is that the smallest prime in the set P is 3. So that means 2 is not there. The third is that both 2 and 3 are in the set. So I think I forgot to say this for the second subcase for the finite one also, that we have similar examples for these particular subcases also in our paper. But of course, I was not able to include all of them. So I'm just stating the subcases here. And then the fourth and the generic subcase for this one is that the smallest prime q in our set of primes is at least 5. So for that particular subcase, where we are assuming that the smallest prime, which is denoted by q, is at least 5, let's define the vector alpha by taking q minus 1 over q times q minus 2 in the Archimedean place. For the place indexed by the prime q, we take -1. And then for all the other places, non-Archimedean places, we're just going to take 0. And then capital N is also going to be equal to q, which is the smallest prime. So then again, we end up with 3 distinct gap lengths, which are denoted by this, this, and this. So again, you can see that all the three numbers are going to be dependent on what our smallest prime q is. So again, in this particular case, we have that the little g and alpha function is equal to 3. So at this point, I think I should say that all the subcases that we have are exhaustive. Like I think this is, we have covered all possible cases of what the set of primes P can be. And for all such cases, we have given an example where the little g and alpha function takes the value 3. So this completes the second part of the proof that this is the best possible bound and it is always attained in any given scenario. And so I think this will be a good point to stop. And I really appreciate this opportunity to give a talk in front of all of you. And thank you so much for listening.
Okay, so let's maybe unmute ourselves and give a round of applause like this. And if anybody has questions, feel free to speak up.
So can I ask a question?
Yes.
So Dima pointed out that on a circle there's no left and right, and sort of clockwise, counterclockwise. Here you have just looked at the distance, so you haven't put an orientation onto how you measure, how you define a nearest neighbor in a certain direction. Could you do that on the adelic torus? So we've done this in the work with Alan, where we looked at higher dimensional generalization and we look at cones. So this should be possible here too, no?
Yes. So for this particular case, we didn't need it, but we have also started thinking about what the theorem should be if we go in higher dimensions. So like for the 2-dimensional adelic torus and onwards. And yes, we do need a notion of what a direction cone will look like. So we have started thinking about how we could, come up with a notion of direction in that case. We still don't have any proper kind of visualization of how that would look like or what it would mean to look in a particular direction. But yes, that is definitely something that we talked about, which we would need in higher dimensions if we want to.
I see. I didn't quite understand. I mean your case here, not a high dimensional version. So just the 1-dimensional adelic situation. Here you also take just the distance. You don't take a directed distance.
Yes.
Or do you?
No, we don't. In this particular case, we have not done that.
So how about here? So just this case you studied here. Have you got a directed distance version of what you've done?
Not yet. So yeah, we have just restricted ourselves to looking at the nearest neighbor. We haven't.
Okay, that's great. Thanks.
But how do you even define this direction in QP? What does it mean?
Yeah, that is what we were not sure about. I mean, like we were thinking about what it could mean, but
it's not totally ordered set. So
yes, that's the problem.
That's interesting.
Yeah.
Okay. Any other comments? Questions? Okay, so maybe since Jan, since you started talking about it, maybe I can ask you, because I'm just not aware of this. So you have some generalizations of the 3-gap theorem to say high-dimensional real tori?
Yeah. So for example, take a 2-dimensional real torus and look at.
I heard about it.
N alpha.
Even.
Sorry, can you hear me?
Yeah, I think I heard about it even maybe from you, but I don't remember details.
Yeah, so you look at just N alpha mod 1 on a 2-dimensional torus, and then you look at the first N iterates of that translation, and you ask what is the number of distinct distances that you can see, and the answer is 5.
I see. So
respect to the Euclidean distance or also the maximum norm. And also this is the best possible. In higher dimensions, we also have upper bounds, but they are far from being best possible.
Interesting.
And as I said, the interesting variation there is, rather than just looking at the distances that you can get, you also can look at directional distances. Like in one dimension, you say to the right or to the left, counterclockwise or clockwise. Here you would look in just cones. So you just say, I'm just going to look at nearest neighbors that fall into a certain directional cone, and you ask, what is the number of distinct distances that you can see there? And then the answer depends on the opening angle of the cone. So if the angle is bigger than pi, you see again finitely many. If the angle is smaller than pi, you see infinitely many distances.
Interesting. Okay, thanks. So this leaves some room for adelic generalizations, I suppose, in the future work. Okay, any other comments or questions? Okay, well, let's thank the speaker again, and thank everyone for participation. So I'll stop the recording now, and we'll look forward to the next talk.